Hello, everyone. I'm Russell Arbore. This work I conducted while I was still at the University of Illinois, and in the fall I'll be starting my PhD studies at Berkeley. Okay, so I'm going to be presenting our work on developing a programming system for hyperdimensional computing applications. So first, what even is hyperdimensional computing? Hyperdimensional computing, or HDC, is just a particular way of solving machine learning problems. So just like you can use deep learning to solve particular machine learning problems, you can also use HDC to solve the same problems. It's mainly characterized by you represent data as very high dimensional vectors, which are called hypervectors. And these hypervectors are typically homogeneous and are in some latent space. And the idea is that all of the operations we're going to be doing on these hypervectors are going to be very cheap. So for example, in deep learning for training models, you typically have a backpropagation stage, which is characterized in part by its very large expense. We'll see in a second what training looks like in the HDC context, but it's much cheaper than that. And then finally, HDC in general is fairly robust to error. So intuitively, because every element in a hypervector contributes roughly the same kind of representational meaning to the overall piece of data, you could get rid of, say, 10% of the elements in a hypervector, and you'll still have most of the meaning of what that data point means. So HDC is in general robust to error both in the inputs and also during processing. HDC has been used for a whole bunch of things, including natural language processing, robotics, voice, gesture, and emotion recognition, graph and hypergraph learning, DNA sequencing, recommender systems, basically a whole bunch of things that are kind of classical machine learning problems you can apply HDC to. So it has very wide applicability. So I want to briefly go over kind of a concrete example of what HDC looks like. So let's kind of consider a very standard like classification task. So we have some data points that we want to group into classes. So the first step of solving this in particular with HDC is to encode our data. This involves taking data that is kind of in whatever original form it came in and converting it into hypervectors. In this case, for this particular classification example, we're going to use what's called random projection coding. That's basically taking some input vector and multiplying it by a random projection matrix. Generating the random projection matrix is a bit subtle, but you can do it offline. So the actual online encoding step is just a matrix multiplication. Next, we need to train a model. In this particular HDC example, all training a model is it just requires one pass through the entire training data set. It's just taking all the representative hypervectors for every training element in a particular class and just adding them all up. That's all you do. And you have what are called representative hypervectors for each class. And then finally, when you actually want to infer the class of new data, you basically do a similarity or dissimilarity check, where you check for your query hypervector which class is it either most similar to or least dissimilar to. And whichever one that is, that will be the class that you're going to infer for the new query. So I just want to emphasize, I am presenting this so that you kind of have an idea of what an HDC application looks like, but this is not at all like the only way you can implement even just classification in HDC, much less any other kind of machine learning task. So there's a very high diversity in different algorithms that are used in HDC broadly. And this leads us into some of the challenges in practice actually developing HDC programs. So if you today want to write a HDC program to solve a particular problem, the first challenge you're going to run into is there's actually a very wide variety of different algorithms in HDC used to solve particular tasks. So the first challenge you'll run into is actually selecting between all these different HDC algorithms. The second challenge is that delivering high accuracy with HDC is rather difficult. So intuitively, because HDC is like much simpler than something like deep learning, you're going to have a harder time developing an HDC system that will deliver a high quality of service on your task. And often this requires tuning in terms of hyperparameters, but also tuning in terms of algorithmic choices. And then finally, the actual hardware targets we want to run these applications on, it's extremely diverse. So we have, I mean, of course, you have like CPUs and GPUs, which are different kinds of generic processors. But additionally, recently, there's been a lot of research into developing HDC-specific accelerators, which have a completely different level of abstraction at the programming level. And what this means in practice is if you want to write a high-performance HDC application today, that means manually writing device code, whether that be CUDA for GPUs or some kind of custom accelerator code that you have for your kind of HDC device. And this makes it much harder to, for example, try a bunch of different HDC algorithms, which, as I pointed out, is kind of a key part of the process. So our approach to kind of addressing these challenges is twofold. So first, we introduce HDC++, which is an embedded domain-specific language for writing HDC applications. And then HPVM-HDC, which is a compiler that will take your HDC++ program and map it onto several different target devices while achieving competitive performance. So first, I'll go over HDC++. Which is basically an extended version of C++ with primitives for representing HDC operations, and also primitives for expressing OpenMP-style parallel loops that are generic and not specific at all to HDC. And this is kind of crucial because in HDC applications, you might have parallelism that's intra-operator, as in a Hamming distance operator. There's kind of inherent parallelism within that calculation. But you also might have inter-operator parallelism. You might have some parallel loop that contains HDC primitives, and we can represent that as well in our language. And then the final thing I'll briefly mention is that HDC++ also exposes approximation knobs for tuning. So as I mentioned earlier, a key part of the process in developing HDC applications is tuning them simultaneously for quality of service and then also performance. So I'll dive into what these knobs actually do in future slides, but just know that with very little code modification and no modification to the underlying algorithm, you can tune these various approximations at the front-end level. Okay, next I'll go over our compiler, which takes in our HDC++ code. It compiles it down into a common intermediate representation. At this IR level, we apply various approximation transformations, and then we pass it through our backend code generators to actually generate target code that we can run. Okay, so first we lower our front-end language into an intermediate representation that is based off of LLVM, which is kind of a common compiler infrastructure. And we extend it with two kind of fundamental things. One are primitives specifically for representing HDC operators. So for example, there'll be a primitive for adding hypervectors or taking the Hamming distance between two hypervectors. And then we also have primitives for generic task and loop parallel primitives in the kind of OpenMP style. And these primitives directly correspond to the primitives in the front-end language. So the lowering process is not too complicated. All right. Next, I'm going to talk about the approximation transformations that our compiler implements. These are indicated for use by the programmer using those approximation knobs in the front-end language. So the first of these that we implement is reduction perforation. Intuitively, the idea behind reduction perforation is since every element in your hypervector is kind of roughly as important as every other element for your overall kind of information representation, we can cut out, say, 20% of the elements in your hypervector, do some computation with it, and still get a mostly accurate result. So all reduction perforation does is for certain reduction operators, such as Hamming distance, just don't process some portion of the vector. So in this example here, we're just processing literally the first half of the vector. And because every element is as important as every other, we can choose what portion of the vector to process that is most efficient on the target processor. The next approximation transformation we implement is called automatic binarization. What this does is it looks for instances of the sign HDC operator, which just takes a hypervector and then for every element maps the element either to -1 or +1, depending on if it's a positive or negative number. And then because after the sign, we know that every element is either -1 or +1, we can represent that with a single bit. So we convert all the output of the sign operator and then all the downstream operators to use a single bit per element rather than whatever element type it was using before. Once we've applied our transformations, we lower them to kind of target device-specific code. We can do this in two ways. So either we can lower a HDC primitive into kind of generic loop level and parallel loop level HPVM IR code, which is basically, intuitively, this is taking a Hamming distance and converting it into the loop that actually implements a Hamming distance. And this is useful for devices such as the CPU, where loops, you can actually lower a loop onto a CPU and that actually means something. Or we can take an HDC primitive and lower it into some device-specific call, effectively, that implements that primitive. And this is useful for devices such as the HDC accelerators, where the level of abstraction for programming is at the HDC operator level. And then additionally, you can take different parts of your application and map them to different devices. So some part of your application you might want to map to the CPU, and that will use the first mechanism. And some parts you might want to map to an accelerator, and that'll use the second mechanism. And these play nice together. Okay, so we evaluated our system on 5 different applications that have a wide variety in different kind of HDC algorithms they use, and for various different purposes. For 2 out of 5 applications, we map them to all 4 devices. That's the CPU, the GPU, and then there's 2 HDC accelerators developed by our collaborators that we target. And then for the other 3 applications, we only target the CPU and the GPU. And that's because these 2 HD accelerators only support a subset of HDC operators, and the other 3 applications just contain operators that you just can't map to the accelerators. So first, I'll go over performance on the GPU. The key takeaway here is not actually necessarily that we're faster than kind of manually written baseline CUDA codes, which is what we're comparing against here. Although that is true in all but one case. The point really here is that we are performance competitive. And what that means is you're not losing any performance by using our programming system. And this should roughly track, since ultimately for targeting the GPU, for example, we are just generating CUDA code at the end of the day. So you would expect for there to be similar performance. Next, we evaluate on the HDC accelerators. In this case, there weren't prior baseline codes that actually implemented the 2 applications on the accelerators. So we compare our code that is compiled and run on the GPU versus our code that's run and compiled on the accelerators, which, by the way, does not require you to change the application at all. It's retargetable. And we see, kind of as expected, that when you run the application on the accelerators, you get significantly better performance than on a kind of comparatively classed GPU. Next, we actually use the approximation knobs I talked about earlier to explore a wide variety of kind of approximation configurations for a single application. So the application before approximation is represented by the black dot, which has a certain kind of inference accuracy, and the relative speed up with itself is 1. The application is a particular classification application that we're running on the GPU. And we see that there's a bunch of different configurations we can explore, and some of them have much worse inference accuracy because you're approximating some key part that you don't actually want to approximate, whereas some of them are much faster and get competitive inference accuracy, which are the ones in green, because for those ones we're actually making kind of the correct choice about what to approximate, so to speak. And the key thing I want to point out here is that exploring each one of these individual points required maybe 1 or 2 lines of code change, and those are kind of to these annotations that tell the compiler what to approximate. They don't change the algorithm at all. And then we also evaluate the programmability. So although a flawed metric, we look at kind of like lines of code that it takes to implement each of these applications. And kind of the point here is that in general, the amount of lines of code it takes to write your application in HDC++ versus the kind of baseline GPU code or the baseline CPU code is roughly equivalent. However, the HDC++ code is retargetable. So this is a single HDC++ application that can target both CPUs and GPUs, whereas the baseline codes, it's one code that targets one device. And then finally, we also, in order to kind of evaluate, at least to a rough extent, how much time you're saving by having this kind of automatic approximation configuration, we had a domain expert manually implement 3 of the approximation configurations in the kind of baseline codes that we compared against. which had a kind of range of different amounts of time it took. The one that took the longest took around an hour of work. This is because for this configuration involved binarization, which means you have to change the element type of a bunch of hypervectors, and also involves changing a bunch of allocations, which is a lot of work. And the key thing is in HDC++, each of these configurations takes seconds to change the line of code. And also, it's correct by construction. So these times also include debugging time for the developer to actually iterate on the baseline that's manually coded. Whereas when the compiler does the automatic approximation transformation, assuming the compiler is correct, the generated code is correct by construction. And then I should also point out that because in HDC++, looking at these different configurations is super quick, that's what enables us to actually try them all out on the previous plot where we showed inference accuracy versus speed up. Some future work is one, we're currently working on targeting more different kinds of HDC accelerators. In particular, some of these expose hardware approximation knobs. So in this talk, I just talked about software approximation knobs that actually transform the code. There are also, for some of these devices, various hardware approximation knobs that we want to exploit. And then the second thing is, although right now it's very easy to explore different configurations, it'd be even better if it was completely automatic. So we're currently looking at ways to automatically do approximation tuning that looks at end-to-end quality of service of your application, and then, of course, performance. So kind of in conclusion, talking aside, we presented a programming system that allows you to develop HDC applications more productively because you only have to develop once, and you can retarget it across devices. And also, you can very easily explore different approximation configurations to tune your application for quality of service and performance. And with that, I'll take any questions.
Thanks.